Across multiple observing nights, astronomers aimed their telescopes at the predicted coordinates for 3I/Atlas, the third confirmed interstellar visitor to pass through our solar system. They consulted the latest ephemeris, the calculated table of where the object should appear in the sky at specific times, and pointed their instruments to those coordinates with sub-arcsecond precision. Then they looked at the images. The object was there, faint but detectable against the background stars. But it wasn't exactly where the predictions said it should be. It was offset. A small amount, fractions of an arcsecond, sometimes just a few tenths, but persistently, and sometimes in a direction that didn't average away when multiple nights were combined. The confusion isn't about whether orbits can be refined. They can. Every new observation improves the solution, tightening the uncertainty ellipse and sharpening future predictions. The confusion is that the residuals, the differences between observed and predicted positions, hint at a behavior that sits right at the boundary between measurement artifact and real physics. For a body moving quickly through crowded star fields at several astronomical units from Earth, even tiny discrepancies can cascade into divergent future positions, shrinking the window of certainty and forcing observers into shorter prediction horizons than they would prefer. The question compounds as the data accumulate. Is the sky map wrong? Are the reference stars used to anchor the position measurements biased or improperly calibrated? Is the timing wrong? Exposure midpoints logged with insufficient precision? Or clock synchronization errors between observatories introducing systematic shifts? Is the orbital modeling complete, missing a small force that nudges the trajectory in ways gravity alone doesn't account for? Or is 3I/Atlas being pushed by something we haven't measured properly yet? Outgassing, radiation pressure, torques from a symmetric thermal emission, forces too subtle to model confidently but too persistent to ignore. The mystery is not dramatic. It's precise. It lives in the residuals, in the careful comparison of where mathematics says an object should be and where photons reveal it actually is. And in that comparison, something isn't matching cleanly. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. To understand why slightly off matters, you have to reframe what a position measurement actually is. It's not a simple dot on a map. It's a time-stamped agreement between clocks, coordinate systems, and geometric transformations. An ephemeris predicts the right ascension and declination of an object at a specific instant in time, usually given in coordinated universal time, to nanosecond precision. But observations aren't instantaneous. They're exposures lasting seconds to minutes, during which the object moves. The reported position corresponds to some moment within that exposure, typically the midpoint, but that midpoint must be calculated correctly, accounting for how the object's motion smears its light across the detector. For a fast-moving target, like 3I/Atlas, an error of even a few seconds in the timestamp can translate into a measurable angular offset on the sky. If different observatories use slightly different conventions for calculating exposure midpoints, or if there are small clock synchronization errors between sites, those discrepancies can create the appearance of positional wander, even when the object's true trajectory is perfectly predictable. Astrometry also depends on transforming pixel coordinates on a detector into celestial coordinates on the sky, a process that requires comparing the target's position to reference stars in the same field of view. Those reference stars come from catalogs, most commonly from the European Space Agency's Gaia mission, which has measured the positions, proper motions, and parallaxes of over 1 billion stars with unprecedented precision. But even Gaia is not perfect. Proper motions, the slow drift of stars across the sky due to their motion through the galaxy, must be extrapolated forward from the catalog epoch to the date of observation. For most purposes, that extrapolation is accurate. But in crowded fields, or for faint stars near the catalog's magnitude limit, small errors in proper motion or parallax can introduce biases. Color terms matter too. If the photometric properties of the reference stars differ significantly from the target, chromatic aberration and atmospheric dispersion can shift the measured centroid in wavelength-dependent ways. And if the target is faint and located near bright stars, The centroiding algorithm, whether it's a Gaussian fit, a flux-weighted mean, or an iterative profile fit, can be pulled slightly toward the brighter nearby source, creating a systematic offset that repeats every time that particular star field is observed. This is where the investigation begins to narrow. If the positional offsets were random, scattered equally in all directions across different nights and different observatories, they would average down with more observations, and the orbital solution would converge smoothly. But if the offsets show structure, if they cluster in a particular direction, or if they correlate with specific observing conditions like air mass, starfield crowding, or the brightness of nearby sources, then the signal is less likely to be pure noise and more likely to be a structured bias, either in the measurement process or in the physics governing the object's motion. Distinguishing between these possibilities requires comparing astrometry from independent observers using different telescopes, different reduction pipelines, and different reference catalogs. If all observers see the same offset, it's likely real. If the offset changes depending on who's measuring, it's likely systematic error in the measurement chain. The background itself is not still, and that instability complicates everything. Modern astrometry anchors to catalogs like Gaia, transforming detector coordinates into the International Celestial Reference Frame, a coordinate system defined by distant quasars whose positions are assumed stable over human timescales. But that transformation is not trivial. Proper motions must be applied. Parallax corrections account for Earth's changing position in its orbit. And the transformation itself involves fitting a model, typically a plate solution, that maps pixel coordinates to sky coordinates using a polynomial or distortion model that depends on having enough reference stars well distributed across the field. In crowded regions near the galactic plane, or in sparse fields far from it, the quality of that fit can degrade. Faint objects near the detection limit can have poorly determined centroids, and if those objects are used as reference stars, the entire coordinate grid shifts slightly. The effect is small, but for high-precision astrometry of a faint moving target, small is not negligible. Different reduction pipelines handle these challenges differently. Some use iterative sigma clipping to reject outlier reference stars. Others apply color corrections based on the known spectral properties of catalog stars. Still others use machine learning or empirical point spread function models to improve centroid estimates in crowded fields. Each choice introduces a potential systematic difference. A faint object sent differently by two algorithms produces two slightly different sky coordinates, and those differences can be coherent, biased in the same direction. If the field geometry or the target's brightness relative to the background is unusual, the mystery sharpens. If the positional residuals correlate with observing conditions, higher at low elevations where atmospheric refraction is stronger, larger in crowded fields, where centering is harder, or directionally biased depending on the orientation of nearby bright stars, then the wonder may be the measurement process struggling against the complexity of the sky, rather than the object genuinely deviating from its predicted path. But there is another possibility, one grounded firmly in physics. The object is being pushed. Small, continuous accelerations, non-gravitational forces, can produce systematic offsets in an orbit that accumulates over time, causing the object to drift away from the purely gravitational trajectory. These forces are real and well documented in cometary science. Outgassing of volatiles like water, carbon monoxide, or carbon dioxide creates jets that exert a rocket-like thrust on the nucleus. Asymmetric thermal emission, where one side of an object heats up in sunlight and re-radiates that heat preferentially, produces a subtle recoil force known as the Yarkovsky effect. Radiation pressure from sunlight, acting on dust particles or on the nucleus itself, pushes objects outward, and the magnitude of that push depends on the object's size, shape, and reflectivity. For an interstellar visitor like 3I/Atlas, whose composition, spin state, and surface properties are largely unknown, these forces are difficult to predict. Solar heating could trigger activity that releases gas and dust, generating thrust that wasn't present when the object was colder and farther from the sun. Spin state evolution, torques from asymmetric outgassing, could change the orientation of jets or the distribution of thermal emission, altering the direction and magnitude of the non-gravitational acceleration over time. Orbit-fitting software can accommodate these forces by adding extra parameters to the model: a radial acceleration component, a tangential component, and sometimes an out-of-plane component, each potentially time variable or dependent on heliocentric distance. When these parameters are included, the fit to the astrometry can improve, residuals shrink, and the predicted positions match the observations more closely. But that improvement comes at a cost. Adding parameters makes the model more flexible, and a more flexible model can fit noise as easily as signal if the data quality or time baseline is insufficient. The test is whether the non-gravitational terms stabilize as more data arrive, converging toward consistent values that remain unchanged when new observations are added. If they do, the case for a real physical force strengthens. If they drift erratically, changing sign or magnitude with each new fit, the extra parameters may be absorbing measurement errors rather than capturing genuine physics. For 3I/Atlas, the orbital arc is still short, the astrometry is sparse and faint, and the non-gravitational solution is not yet definitive. It fits the data better than a purely gravitational model in some cases, but the parameters carry large uncertainties, and their physical interpretation remains ambiguous. Plausible drivers exist within known physics. If 3I/Atlas has residual volatiles near its surface, ice deposits that sublimate under solar heating, those volatiles could produce jets strong enough to generate measurable thrust. The jets wouldn't need to be visible. Faint gas emission, invisible in optical imaging, can still carry enough momentum to perturb an orbit. Dust production alters the momentum budget too. Grains lifted off the surface carry momentum away. And if that loss is asymmetric, concentrated in certain directions due to rotation or topography, the nucleus recoils. Radiation pressure on dust in a tenuous coma can also contribute, though the effect on the nucleus itself is smaller, unless the coma is optically thick enough to shadow the nucleus or redirect sunlight asymmetrically. All of these mechanisms depend on the object's properties, its size, which controls the surface area available for heating, and the gravitational binding of material, its composition, which determines which volatiles sublimate at which temperatures, and its spin state, which controls which surface regions are illuminated and for how long. For an interstellar object, none of these properties are well constrained. We don't know if 3I/Atlas is a few hundred meters across or a few kilometers. We don't know if it's ice-rich or refractory. We don't know if it's spinning rapidly, tumbling chaotically, or rotating slowly. That uncertainty propagates into the force model, making it difficult to predict what acceleration should be expected, and whether the observed residuals are consistent with activity-driven thrust or require a different explanation. The investigation becomes a contest between two regimes: large, obvious gravitational perturbations from massive bodies like Jupiter, and tiny, continuous accelerations from non-gravitational forces. Both are real. Both are modeled in the ephemeris. But the interplay between them can be subtle. Jupiter's gravity reshapes trajectories in predictable ways. Its influence is calculated from its known mass, position, and the object's closest approach distance. Those effects are baked into the orbit solution. But if the initial conditions, the object's position and velocity at some reference time, are not known precisely, or if there's uncertainty in the closest approach distance because the orbit isn't fully resolved yet, the gravitational perturbation can be slightly wrong. A small error in the pre-encounter trajectory becomes a larger error post-encounter because close approaches amplify sensitivity. Small differences in approach geometry produce large differences in the deflection angle and the outbound velocity. At the same time, a small sustained non-gravitational acceleration, acting over weeks or months, can cause a growing displacement along the object's path, and a long-track error that looks timing-like rather than directional. That error can mimic or mask gravitational effects, making it hard to distinguish whether a positional offset is due to an underestimated Jupiter perturbation or a steady, unmodeled thrust. The diagnostic is geometric. If the displacement is primarily along the direction of motion, leading or lagging the predicted position, it suggests a timing or a long-track acceleration issue. If the displacement is perpendicular to the path, cross-track, in right ascension or declination separately, it points toward mismodeled direction, an incorrect orbital inclination, an unaccounted torque changing the plane of motion, or a measurement bias that shifts coordinates systematically. For 3I/Atlas, the residuals show both components, complicating interpretation. Some nights, the object appears slightly ahead or behind where it should be, consistent with a small radial acceleration, or a timing error. Other nights, it's offset laterally, suggesting either a cross-track force or a reference frame problem. The pattern isn't random, but it's also not cleanly periodic or monotonic, leaving multiple explanations plausible and none yet conclusive. There's another layer to this. Photometry can bias astrometry. When astronomers measure the position of an object, they're really measuring the centroid of its light distribution. For a point source, a star or a distant quasar, that centroid is well-defined and stable. But comets and active bodies don't present clean point sources. They have comet, tails, jets, and asymmetric brightness distributions that change with viewing geometry, solar heating, and activity level. If 3I/Atlas has developed even a faint, asymmetric coma, material preferentially emitted in one direction due to rotation or localized outgassing, the measured centroid will be offset from the true position of the nucleus. That offset can be systematic, repeating every time the same asymmetry is viewed from the same angle. Different observatories using different aperture sizes, different filters, or different centroiding algorithms might measure slightly different positions because they're weighting the light distribution differently. A larger aperture captures more extended coma. A smaller aperture isolates the nucleus better, but loses signal to noise. A red filter might see less scattered dust than a blue filter, shifting the measured center if dust scattering is color-dependent. This reframes the mystery. The object might be exactly where physics predicts, but its light is not distributed in a way that makes its location easy to define. The nucleus could be at the gravitational center of mass, but the photocenter, the brightness-weighted average position, could be offset by tens or hundreds of kilometers projected onto the sky, corresponding to fractions of an arcsecond depending on distance. If that offset varies with time as the coma evolves, or as viewing geometry changes, it would produce apparent positional residuals that have nothing to do with forces on the nucleus, and everything to do with where we measure position when the object isn't a point. Testing this requires comparing photometry across different apertures and filters, looking for correlations between brightness asymmetry and positional offset. If the offset grows when the coma is brighter or more extended, and shrinks when the object appears more point-like, that supports a photocenter bias. If the offset is independent of photometric behavior, it argues for a real trajectory deviation, or a measurement systematic unrelated to the object's light distribution. And then there's the human system around the data. Ephemerides are living documents. They are updated as new observations arrive, as orbital fits improve, as outliers are identified and removed or downweighted. The public-facing ephemerides, those published in bulletins and used for planning observations, are not always the latest internal solutions used by active research teams. There can be a lag. A team might have new astrometry that significantly revises the orbit, but the update hasn't been propagated to the official prediction services yet. Delays in reporting, processing, and cross-checking can cause the published ephemeris to be hours or days behind the best available fit. That lag can make the object appear off, when in reality, the prediction being used is simply outdated. Weighting choices matter too. How much confidence is assigned to each astrometric point, whether certain nights are flagged as suspect due to weather or instrumental issues, and whether early observations are downweighted in favor of more recent, higher quality data. Each of these decisions affects the orbital solution, and different teams can arrive at slightly different answers from the same raw measurements if they make different methodological choices. Covariance is another subtlety. The uncertainty in an orbit is not a single number but a multi-dimensional shape in parameter space, describing how errors in position, velocity, and other parameters are correlated. The object isn't off at a single point. The uncertainty ellipse is evolving as new data constrain some parameters better than others. Early in the observational arc, the uncertainty along the direction of motion can be much larger than the uncertainty perpendicular to it, and that asymmetry changes as the arc lengthens and the geometry improves. The predicted position is the center of that uncertainty distribution, but the true position could be anywhere within it. If new observations consistently fall near the edge of the predicted uncertainty region, it suggests the model is missing something, either a real force or a systematic bias in the measurements. But if they scatter within the uncertainty, the model is performing as expected, and won't stay where predicted is just the normal process of refining an orbit under uncertainty. Yet when the best fit solution keeps shifting in a consistent direction, even after updates, it stops feeling like normal refinement. It starts looking like a persistent, unresolved cause, something the model isn't capturing fully. That tension is where the investigation sits, between measurement artifact and real physics, between timing errors and thrust, between reference frame problems and activity-driven perturbations. The data don't yet decisively favor one explanation over the others. The residuals are small enough that systematic errors could explain them, but they're structured enough that dismissing them as pure noise feels premature. And they persist across enough observing epochs and independent sites that a single bad night or miscalibrated catalog can't account for all of them. Looking forward, the opportunity to resolve this ambiguity is narrowing. 3I/Atlas continues outbound on its hyperbolic trajectory, receding from the Sun and Earth, dimming as distance increases. Within weeks to months, it will fade below the detection limits of most ground-based surveys, and the astrometric arc will end. Future observations will require the largest telescopes, space-based platforms, or serendipitous redetection by wide-field surveys like the Vera-C. Rubin Observatory, which will track faint moving objects with unprecedented cadence and sky coverage once operational. For 3I/Atlas specifically, the dataset we collect now, the astrometry, the photometry, the residuals, and their patterns, may be all we have to work with. If non-gravitational forces are present, the longer the observational arc, the more cleanly they can be separated from gravitational effects and measurement noise. But if the object fades before the arc is long enough, the ambiguity will persist, and the question of why it won't stay exactly where predictions put it will remain open. What we're left with is a reminder. The universe often whispers in residuals, small discrepancies between model and measurement that force better physics, better error budgets, better understanding of the instruments and the assumptions underlying the analysis. A tiny positional mismatch can carry enormous meaning, not because it proves anything exotic, but because it reveals where our models meet the limits of measurement, where precision astronomy confronts the complexity of real objects moving through real space under forces we infer but cannot see. For 3I/Atlas, the central question remains unanswered. Is the object deviating from a purely gravitational path due to subtle thrust from outgassing, thermal forces, or interaction with dust and radiation? Or are we watching the boundary conditions of our coordinate systems, our timing precision, and our centroiding algorithms, struggling to define a position for a faint, possibly asymmetric target, moving rapidly through crowded star fields? Both are scientifically meaningful. Both require follow-up. And both remind us that in precision astrometry, the most honest result is often not a triumphant answer, but a better understanding of what we do not yet know, preserved through the discipline to keep observing, keep refining, and keep asking why the numbers refuse to agree.